so you know you need high availability in the network. And you've decided that ASA clustering is worth a closer look. The good news is that I can help you with that. Clustering is one of the best methods of high availability for the ASA. All ASAs in the cluster are active, and if you have the 5585s, they scale well. In this video, we'll have a look at how ASA clustering works and how traffic flows through the cluster. If you'd like a refresher on other types of HA, I recommend checking out my ASA high availability video. Each ASA in a cluster is a cluster member. Try to think of the cluster as a single unit. Sure, it's made up of ASAs, but it behaves as a single unit. In this unit, one of the ASAs is the brain. It's called the primary, and it performs most of the control plane tasks. If you're not familiar with control plane functions, think of them as any traffic sent to or from the cluster. This is different to traffic that is sent through the cluster. An example of this is OSPF. All other cluster members are secondary units. All cluster members form the data plane. This means that they all forward traffic. Some features will only work on the primary ASA, as they are control plane features. These features are called centralized features. An example of this is OSPF. The primary participates in dynamic routing and builds a routing table. The primary ASA replicates the routes to the secondaries. The secondary ASAs never form neighbor relationships with other routers. The cluster members decide on the primary by an election. You can set a priority on each ASA to influence the election. The lowest number is the highest priority. If there's a tie, serial numbers are used to decide on the primary. There's something that I really need to emphasize though. There is no preemption in a cluster. If a member joins with a better priority, it does not automatically become the primary. An election is only held if the current primary fails. Imagine what would happen if we did have preemption. Remember how I said that some features are centralized? If the primary were to change, all those centralized connections, such as VPNs, would drop. They would then have to be re-established with the new primary. Not exactly ideal, is it? Remember that we like to think of the cluster as an entire unit. But what happens if a member in that unit fails? Well, quite simply, it is removed from the cluster. But an entire member failure isn't the only threat to the cluster. Interfaces in a cluster are critical. If an interface on a cluster fails, that will also cause the member to be removed. This is true of data interfaces as well as the cluster control link. After repairing these interfaces, the member can rejoin the cluster. As a final note, you will find documentation that refers to master and slave roles. These are the same as primary and secondary in the newer documentation. You can think of each cluster member as a line card in a chassis. Each line card is connected by the backplane. In the ASA cluster, a group of ports are configured on a separate network called the cluster control link. This is the cluster's backplane. The CCL carries control messages such as elections, config replication, and health monitoring. It also carries some data traffic. This includes queries about which member a particular packet should be delivered to, but we'll look at that more later. The CCL uses dedicated ports that connect to a switch. If the CCL goes down on a member, the member is removed from the cluster. Even in a two-member cluster, the switch connection is mandatory. Why do you ask? Well, the CCL is a critical part of the cluster. Imagine for a moment that the ASAs were directly connected. What if the CCL from one member were connected directly to another and one member ASA failed? The CCL would go down on both members. The second member would also be removed from the cluster and the entire cluster would fail. Connecting to a switch prevents this. If an ASA fails, the link to the switch goes down. but the links to the other ASA will stay up. To enhance redundancy, use VPC or a VSS connection. Every packet that passes through the cluster is classified into a connection. Source and destination IP addresses, ports, and protocols form this classification. The cluster tracks each connection. This is so each connection can be handled by a single ASA member. To do this, there are 3 connection-oriented roles that the ASA may hold. The first is the owner role. Each connection is owned by a single member. All packets from a connection must pass through the connection owner. When the first packet from a new connection arrives, the member to receive the packet becomes the owner. It begins tracking the connection. A single ASA may own thousands of connections. When the owner tracks a connection, it sends a backup copy of the connection details to another ASA. This ASA is called the director. The director maintains a backup of the connection state. There is only one director per connection. To select a director, the owner calculates a hash of the connection details. This makes it easy for other members to find the director later. A member may get a packet for a connection that it doesn't own. This member is called a forwarder. The forwarder calculates the hash value for the connection to find the director. The director may also be a forwarder. The forwarder then queries the director to find the owner. It forwards the packet to the owner to process. If an owner were to fail, you may think that the director will automatically become the new owner. If you thought that, you'd be wrong. Instead, the first member to receive the packet from the connection will become the new owner. It will first query the director to get the connection state information. It then resumes forwarding packets. Cluster members are connected to switches. These switches need to decide which cluster members to deliver packets to. There are a few different ways this could be done. The first is with an ether channel, which is the recommended solution. As shown here, this could be a connection to a single switch. A better way is to use VPC or VSS for redundancy. In this solution, normal ether channel load balancing methods allocate packets to cluster members. If you need a refresher on how this works, have a look at the ether channel article on the Network Directions site. The second option is to use policy-based routing. This option uses ACLs and route maps to direct traffic. ECMP is the third option. This is where switches and the cluster members run a dynamic routing protocol. Each ASA appears to be a path in the destination, where each path has an equal cost. The routing protocol load balances traffic the same way it would for any ECMP topology. The final option is new and is called Intelligent Traffic Director, or ITD. This is Cisco's proprietary load balancer on the Nexus platform. It's like PBR, but it's more granular and automated in the way it allocates traffic. When selecting a method, try to pick one that will deliver packets from a connection to the same ASA member every time. This prevents the needs for forwarders to pass packets over the control link. Where possible, try to avoid using NAT. I know what you're thinking. We need NAT. There's no getting around it. Well, that's probably true. But consider what happens with NAT. By its very nature, NAT changes IP addresses and ports. Generally, load balancing is based around IP addressing and ports. This means that load balancing may become asymmetric. If this happens, the packet will be forwarded over the cluster control link. All data interfaces in a cluster must be in the same mode. The mode can be set to Spanned-Etherchannel or individual. Spanned-Etherchannel may use a single switch or a pair of switches. The recommended method is to use a pair of switches with VPC or VSS. From the ASA perspective, all interfaces are bound to a single logical link. This is like Etherchannel, but across all devices at once. The ASA uses a modified version of LACP called CLACP to make this possible. The switch pair appears as a single switch to the ASA, and the ASA cluster appears as a single ASA to the switches. Spanned-Etherchannel is recommended for two main reasons. For one, it doesn't require complex configuration. Also, it has very fast convergence already built in if there's a failure. Individual interface mode is a bit different. Interfaces are not bundled into a virtual interface. In fact, each interface has its own IP address. Connected routers or switches pass packets to the ASA interfaces using PBR, ECMP, or ITD. As individual interface mode uses IP addressing, transparent mode is not supported. Management interfaces are also set to either Spanned-Etherchannel or individual interface mode. This mode does not have to match the data interfaces. It is recommended to use individual interface mode for management. This means that each ASA can have its own management IP. This is useful for troubleshooting issues on a specific member. In either case, console connections are still available. Now that we've covered the theory, be sure to check out the cluster configuration video to see it all in action. Also, there's a lot more information in the full article, so it's a good idea to have a read of that as well. If you've enjoyed the video, or if it's been helpful to you, please like the video or drop a comment below. Subscribe to the channel or follow me on Twitter to be notified of new videos or articles. Thanks again for watching.